Hope you had a great weekend. We're going to finish up our discussion of HOMO and LUMO today, give you some sense for how useful the concept is, and then we'll move on to chapter 2. All right, so you've been taught how to identify HOMO and LUMO in an organic molecule. In general, you care about the HOMO of the nucleophile, the molecule that has extra electron density, and the LUMO of the electrophile. And at this stage, you're going to be told what the nucleophile is and what the electrophile is. And then over time, you'll build up some intuition so that you can figure that out on your own. For now, let's just do some examples. For example, what I'm going to draw for you here is an electrophile. And so you care about what the LUMO is. Now, if you look at this BH3, I will tell you that the LUMO is an empty p orbital, and that is a non-bonding p orbital, meaning this is not an antibonding orbital at all. Now, there's been a popular question is, how do I know that a molecule has an empty p orbital? And the answer is, figure it out. But that's not that helpful at this stage, so here's how you figure it out. First, you look at the molecule and you notice that because BH3 doesn't have any formal charge, that boron must necessarily only own 3 electrons. Right? Boron has 3 valence electrons. If it only owns 3 electrons, then it has a neutral formal charge. That tells you that there is no lone pair on boron. Boron is therefore only surrounded by 3 groups, so it must be trigonal planar sp2 hybridized, and each of the sp2 atomic orbitals on boron is involved in these BH sigma bonds. Left over, unhybridized and without anything in it, is the p orbital, and that's why I say that it is empty. So that is one of the 2 times that you'll find an empty p orbital, on a neutral boron that is attached to 3 different things. The other time you'll find an empty p orbital is actually in what we'll call a carbocation, and this is where there is a carbon attached to 3 things with a positive formal charge on the carbon. For carbon, which normally has 4 valence electrons, the positive formal charge tells you that this carbon only owns 3, therefore it has no lone pair. Like BH3, it is trigonal planar sp2 hybridized. Like BH3, each of the sp2 atomic orbitals from carbon are involved in one of the 3 sigma bonds between carbon and hydrogen, leaving the empty, unhybridized, non-bonding p orbital on the carbon. Yes?
How do you know if the bond or if it's going to be hybridized?
I mean, how do you know if it's going to be hybridized? A p orbital is, by definition, not hybridized. It wasn't involved in the sp2 hybridization.
Sorry, how do we know that boron and carbon in that case are going to have hybridized orbitals?
You know that boron and carbon are sp2 hybridized from geometry. You recognize that they're each surrounded by only 3 things based on what I told you. They are trigonal planar, that's the geometry, and therefore to explain trigonal planar geometry they must be sp2 hybridized, which means that boron has, or carbon have, 3 sp2 orbitals and 1 p orbital left over. Okay, right. So those are 2 situations where you can have an empty p orbital. That's the reasoning. Now let's show you what a nucleophile might be, and we're just going to pick a boring one, and that is water. And what do you think the HOMO is on water? It's got to be the lone pairs on the oxygen, the ones that aren't involved in a bond. All right. If you wanted to draw what the lone pair looked like on water, you certainly could. I usually don't bother because once I know it's a lone pair and I've drawn the lone pair, that's all the information I need. If you wanted to say, hey, the lone pair on water is in an sp2 type orbital and so is the other one, that would be just fine, no problem. I generally don't bother drawing them though, because it's obvious once you draw the lone pair. Now, if you were going to predict what happens in this reaction, the HOMO of the nucleophile attacks the LUMO of the electrophile. So we draw an arrow starting with electrons in the HOMO of the nucleophile to the atom that has the LUMO of the electrophile. Here, the LUMO is an empty p orbital. It is only on one atom. So, and that arrow that we draw indicates the formation of a new bond, in this case, a sigma bond. And so you can draw the product for these two reactions as a new bond between boron and the oxygen nucleophile. And once you draw in the rest of the atoms, you see that the boron will need a negative formal charge and the oxygen will need a positive formal charge. For the carbocation here as an electrophile, you would see that you form a new carbon-oxygen bond, that the carbon needs no formal charge, but the oxygen does need a positive formal charge. Okay? And in red is the new bond that we formed. The new bond used to be the lone pair on the oxygen. Now it's in a bond. It moved lower in energy because bonds are lower in energy than lone pairs. Questions about that? Yes?
Do we have to worry about the hybridization?
Oh, let's see. There's two of you. Let's have you first and then you.
Do we have to worry about the hybridization of the oxygen at all?
Do you have to worry about the hybridization of the oxygen when? Before, after, during?
Before.
Okay. Do you have to worry about what type of hybrid orbital these lone pairs are in? Not really. If you want to draw it, you sort of do, because you need to draw something reasonable. If you draw an sp3 hybridized orbital, that's reasonable. I'll tell you, though, that actually organic chemists don't worry about lone pair hybridization very much. There's some cases where we do, but for the most part, we don't worry about it. All right, and this, yeah, you go ahead. Answer your own question. Great. Less work for me to do. Perfect. Others? Yes?
So there was two sets of lone pair before the reaction. One lone pair formed the bond. Where is the other one?
The other one, good. There were two lone pairs before the reaction. One formed the bond. The other's still on the oxygen. Good. Other, I saw like two other hands. Go ahead.
This, I think you probably already explained this, but in like the molecular orbital diagram, where there's always like the bonding and non-bonding orbitals, but
Yes.
in the lone pair, there's not another non-bonding orbital. Can you explain that?
Right. So, not totally sure I understand the question. For every bond, there is a bonding orbital and an anti-bonding orbital. For lone pairs, there's not, because they're not involved in bonds. And for empty p orbitals, there's also not, because they're not involved in bonds. Yeah?
When we have these reactions, does the nucleophile end up being positive most of the time?
When we have these reactions, does the nucleophile after the reaction end up being positive most of the time? No. If I had chosen a nucleophile that was negatively charged, it would have been neutral here. Okay, others? Okay, one thing I want to point out here, which is useful, is the identity of the LUMO often tells you what you need to do after that first arrow. The first arrow always goes from HOMO to LUMO, but then sometimes you have to do something else. In this case, you don't, because the LUMO is not an antibonding orbital. It is a non-bonding atomic orbital. It's an empty p orbital. When the LUMO is an empty p orbital, there's no other arrow to draw. You simply draw the line from HOMO to LUMO, and that's your new bond. Let me show you an example of a reaction where there is something for you to do after the fact. So let's take this alkene. And let's react it with HCl. I will tell you that HCl is the electrophile. If something actually has the name acid in its name, it might be the electrophile. That's one hint. And then this molecule is the nucleophile. It's called an alkene because it has a carbon-carbon pi bond. So remember, for the nucleophile, we care about the HOMO. For the electrophile, we care about the LUMO. What is the HOMO of the nucleophile? It is the carbon-carbon pi bonding orbital. You know it's that because there's no lone pairs and because pi bonds are less stable than sigma bonds. If we were to draw that on this molecule, what would that look like? You would have a large lobe above the plane of the page and another large lobe below the plane of the page. They would have opposite wave function sign, and that's one way that we could draw a pi bonding orbital. Now, how about the electrophile? For the electrophile, we care about the LUMO. What is it here? Kind of boring. It's the sigma star. That's the only empty orbital in this molecule. There's a hydrogen chloride bonding sigma orbital and a corresponding hydrogen chlorine sigma star antibonding orbital. There's no other empty orbitals. There are 3 lone pairs on the chlorine. We don't care though, because this is the electrophile, and all we care about for the electrophile is the LUMO. If we were to draw the LUMO for this molecule, here's what it would look like: a lobe on hydrogen leaning away from the node, and then a small lobe on chlorine pointing towards the node, and a larger lobe leaning away. And you would shade things to have correct wave function sign. All right, so you've got another nucleophile and another electrophile. Unlike before with BH3 or the carbocation, for HCl, the LUMO is on 2 atoms, and the LUMO is an anti-bonding orbital. When the LUMO is on 2 atoms, you have to ask the question, which of those 2 does the HOMO attack? Because you've got a choice. And to make that decision, your best bet is always electronegativity. Electronegativity will tell you chlorine is more electronegative than hydrogen. That means that the hydrogen-chlorine bond is polarized towards the chlorine, that chlorine has a delta minus on it, and the hydrogen has a delta plus on it. That tells you that the hydrogen is electron poor. In general, nucleophiles are nucleophiles because they are electron rich. So we're going to draw the arrow from the electron rich nucleophile to the electron poor the electron poor atom of the LUMO. Does that make sense? So when you have a choice, when the LUMO is on 2 atoms, use electronegativity to identify which of those 2 atoms is most electron poor, and then draw the arrow there. So I'm going to draw the arrow from the pi bond in the pi carbon-carbon pi bonding orbital to the hydrogen. Now, because this is an anti-bonding orbital, I have to break the hydrogen-chlorine bond. The other clue that I have to do that is just to recognize, if I don't, I now have 2 bonds to hydrogen, and that breaks. Yes, it's not the octet rule for hydrogen, but basically hydrogen only has space for 2 electrons in its valence shell, and you'd have too many on hydrogen. So this is why it's useful to know what an antibonding orbital is, because it tells you when you must break a bond. You fill the antibonding orbital, you break the hydrogen-chlorine bond, and the electrons in that bond go to the other atom, the one that you didn't attack. So the first arrow here signifies the formation of a new sigma bond, and this arrow signifies the breaking of a sigma bond. So let's draw the products. One of those is Cl minus, it left, and this lone pair on it came from the HCl bond. Because Cl minus left, we will often call it a leaving group. We're going to use that language. The leaving group is the thing that takes the electrons from the sigma bond that was broken. Over here on the nucleophile side, we got another problem, and that is we used the electrons from the carbon-carbon pi bond to attack the hydrogen. We need to make a new sigma bond, but you got two carbons, carbons 1 and 2. So we're going to have to decide which one gets the new sigma bond to hydrogen and which one doesn't. Fortunately, go ahead.
Said it wouldn't matter in this case because they have the same electronegativity. Whereas
Good, yeah, fortunately in this case they're identical, so it doesn't matter. You can give it to carbon 1 or carbon 2, it doesn't matter. Later on in chapter 10, it will matter, and we'll show you how to choose. It's actually not hard, there's some basic principles, but it's better to wait to introduce those till later. So let's just say that the new carbon-hydrogen bond goes on to carbon 1. This is the new sigma bond. This is carbon 1. And then here's the other hydrogens on carbon 1. What has to be present now on carbon 2? Yeah, got to be a positive charge. Why? Because carbon 2 used to be sharing those electrons in that pi bond, and now it's not. Okay? So notice how once you have HOMO attack LUMO, and then you deal with the aftermath of that based on whether the LUMO was an antibonding orbital or not, notice that these arrows are the instructions for what the products are. If you know how to have HOMO attack LUMO, you can predict what the products are. Okay, are there questions about how we did that? Yeah.
Just confirming that carbon 1 would then have tetrahedral geometry. Right?
Exactly. So carbon 1 is no longer trigonal planar because it's surrounded by 4 things. Good. Another, yes?
So if that had been on the hydrogen chloride, if that, like, if the new molecule that was attacking it, if it didn't break the octet rule, would it just be added to that molecule?
Right. So is there any way to have a nucleophile attack hydrogen and not break the octet rule? No. But what you're asking is exactly this situation before. We have the nucleophile attack and it doesn't break the octet rule, so there's nothing else to do. Yeah, go ahead.
would carbon 1 be positive because we lost an electron and gave it to chlorine? Or no?
Would carbon 1 be positive because we lost an electron and gave it to chlorine? No. These two electrons in this pi bond that carbon 1 was sharing to begin with, and remember, carbon, you can tell it's charged because carbon owns all of its lone pairs and half of the electrons in its bond. So look here, carbon has 4 bonds, owns 4 electrons. After the reaction, still 4 bonds, still 4 electrons. Carbon 2, though, now only has 3 bonds. But yeah, technically carbon 2 is positively charged because it used to be involved in a pi bond and now it's not. Yeah.
So when you drew the new sigma bond from carbon 1 and 2 all the way to the H, you drew like the arrow with the arrow pointing to the H.
Yeah.
That just signifies that H is going to go back to the carbon 1 bond.
So this arrow signifies that the electrons in the pi bond between 1 and 2 attacked the LUMO at hydrogen. That's going to form a new sigma bond. Yep. Now you got to choose whether it goes from 1 to 2, and here there's no preference because they're identical. You get the same thing either way. Yeah.
On the antibonding orbital with HCl, why does the Cl have 2 lobes?
Why does the Cl have 2 lobes? Remember, the bond for HCl comes from overlap of a 1s orbital on hydrogen with, you could think of it as an sp3 orbital on chlorine. And that's overlap in phase where there's no cancellation. If they overlap out of phase with opposite wave function sign, that's when, oops, sorry, trying to do this too fast. So if they overlap out of phase with opposite wave function sign, you get cancellation. And that's why the orbital is leaning away on the hydrogen, because it's been canceled out here. And that's why this lobe is smaller, because it's also been mostly canceled out. Yeah. Other than that, I mean, that's sort of more of a mnemonic device for remembering. If you want to just remember for antibonding orbitals, you, on chlorine and carbon and so on, you draw it almost like an sp3 orbital backwards. Yeah.
Two questions. The first question, for our final product, do we need to worry about like whether hydrogens are coming like going to the page or
For the final product, do we need to worry about here whether the hydrogens are coming out of the page or towards us? As long as you know this carbon is sp3 hybridized, that's fine. Now, I haven't drawn dashes or wedges here, and it would have been totally fine for me to do so. I cannot as well, as long as everybody knows I'm talking about an sp3 carbon. But you're right, probably for completeness, we would do something like this. Oh, second question.
My second question was for the hydrogen chlorine bonds. Can you explain like the filling of antibond orbitals and how it broke apart with like the molecular diagram that we draw?
Sure. Why does this break apart?
Yeah.
So anytime you have a HOMO on your nucleophile, and I'm just going to draw the HOMO, and then a LUMO on your electrophile, I'm just going to draw the electrophile like this, and this is the LUMO. When the HOMO attacks the LUMO, it's really like you bring two orbitals together and you mix them. You get a new sigma bonding orbital, and then you get a new anti-bonding orbital, a new sigma star. The reason this bond has to break, though, and that bond allows the electrons in the HOMO to move from higher energy to lower energy. So the electrons that were in this pi bond are now in a sigma bond where they're lower in energy. Now your question is, why does the HCl bond have to break? Two reasons. First, I'm making a new bond to hydrogen, and if I don't break the HCl bond, hydrogen is surrounded by more than the allowed number of electrons. Second reason is this is an antibonding orbital, and anytime you populate an antibonding orbital, you break the bond. The part that you're not seeing over here, and this is just shorthand. I haven't thought of a systematic way to do this where it's going to make a lot of sense. The LUMO is itself a sigma star, and there is itself down here a sigma bonding orbital in the hydrogen chlorine bond. When I do this, when I now involve what used to be the sigma star in a new bond, then chlorine takes these electrons that were in the hydrogen chlorine bond and it just leaves. So the electrons from the HCl bond become a lone pair on chlorine. The electrons from the pi bond become this new sigma bond. Yeah?
So in the product, is carbon-2 a carbocation?
Carbon, in the product, carbon-2 is a carbocation. Good.
So what did that make it essentially create the anti-carbon or LUMO?
Yep. Excellent. So you are seeing that this product that we have looks like an electrophile because it is a carbocation. And you are noticing that the LUMO would be an empty p orbital on carbon-2, and then Cl- looks very much like a nucleophile. And the HOMO is, boring, just the lone pair on chlorine, there's nothing else. So make a prediction. What do you think could happen here? Backwards reaction where, well, it doesn't actually go, it's a forwards reaction in the sense that it doesn't go back to starting materials. If chloro attacks the empty p orbital on carbon-2, you now have a new product. That arrow signifies the formation of a new sigma bond. I'm just going to draw real briefly the empty p orbital on carbon-2. That's the LUMO that you're referring to. When chloro attacks, we attack that empty p orbital, and the product should be this, where we now have a new carbon-chlorine sigma bond. Now, how did you know that you didn't have to do anything other than form that sigma bond? We knew that because the LUMO is not an antibonding orbital. Okay? So HOMO attacks LUMO can actually lead you to predict multiple steps of a reaction. Go ahead.
Is this similar to like acids and bases and conjugate acids?
Is this similar a little bit to acids and bases and conjugate acids and bases, so on? It is, though I'll show you the connection a little bit later. Okay, what else? Yeah.
So, why is the LUMO and the hydrogen chloride an antibonding orbital?
Why is the LUMO on HCl an antibonding orbital? You're right. If we look at HCl and we think about what's present, all I've got in HCl is one HCl sigma bond, and then I have 3 lone pairs. If I draw that on an energy diagram, here is the HCl sigma bond. Here, about my break-even point, are the 3 lone pairs, and then up here is the hydrogen-chlorine sigma star antibonding orbital. That is actually the only empty orbital in the molecule, and so it has to be our LUMO.
Is this a good way to figure out LUMOs and just drawing out this energy field?
Yeah, you can do it this way, and that'll work. The other way to look for LUMOs is just to start with look for empty orbitals that are as low in energy as possible. An empty p orbital first, and if there's not that, you look for a pi star, and if there's not that, you look for a sigma star. Yep. Okay, others? Yeah.
Would you ever just like on that first reactants, would you ever just like draw all steps of that, or do you have to draw 2 steps of the reaction?
Right, so you're saying, would I go here straight? No, you won't. You have to do it stepwise, and that is, HOMO LUMO tells you that, right? The opportunity for the chloro to come back in doesn't happen until you created this intermediate. Yeah. Okay. Now, somebody in the 8 o'clock hour asked a question. They looked at that product and they're like, hey, that product has, oh, and by the way, that 2-step reaction, step 1 and step 2 together, those are called an addition reaction. Because if you look at what we did relative to the alkene, we attached a hydrogen and a chlorine in the place where the pi bond used to be. So, and that's something you're going to get to in chapter 10, but you already have tools to understand the mechanism. I want to also point out, somebody in the 8 o'clock hour looked at that and said, hey, wait a minute, there is a carbon-chlorine sigma bond, and you just told us that those carbon-chlorine sigma bonds are weak. They are weak because of the size of chlorine. Chlorine is larger than carbon, and carbon-chlorine sigma bonds are longer than carbon-carbon bonds. Longer bonds are weaker. So if you look at this molecule, you would say that the LUMO, there's no empty p orbital, there's no pi star. The LUMO is probably some kind of sigma star antibonding orbital, and you're going to choose the weakest sigma bond to have the lowest energy antibonding orbital. And so you would conclude that the carbon-chlorine sigma bond is the LUMO here. And we could draw that. You would draw the node in between the 2 nuclei. You would draw little lobes pointing towards the node and larger lobes pointing away from the node. And so somebody in the 8 o'clock hour said, hey, isn't that also an electrophile? And I said, yes, whether or not it goes on to react depends on what you put in the reaction. This molecule itself is stable on its own, but you could use it to do a subsequent reaction if you provided a nucleophile. Yeah?
If we have a large atom like chlorine in it, is it safe to usually say that the LUMO is an antibody?
If there's a chlorine bonded to a carbon, is it safe to assume that the sigma star is going to be the LUMO? If there's no pi star, yeah. Yep, good, yes?
Is there a reason why on that molecule that you drew, the bonding there, is there a reason why the big orbital is not
Is there yeah, there is a reason why we put the large lobes pointing outward and the small lobes pointing inward, and it's literally because of the node here. That signifies that when we brought the two orbitals together, they canceled themselves out and they're smaller in the middle. Yeah?
So if we go back to the first reaction, I'm not sure if I understand energetically how things are happening. So, does the HOMO of one molecule always have to be higher in energy than the LUMO of the other when reactions occur to make the solution more involved?
Yeah, great question. Does the HOMO always have to be higher in energy than the LUMO of the electrophile in order for the reaction to happen? No, not at all. So here is, let's just be really generic. Here is the HOMO of our nucleophile, and here is the LUMO of our electrophile. As long as they're close enough to overlap with each other in energy, and by that I mean the reaction gets more and more unfavorable if they're like this far apart. If they're this far apart, eventually you don't see a reaction. The follow-up question is going to be, how do I know how far apart needs to be in order for a reaction not to occur? That we're going to have to answer on a case-by-case basis and develop some more intuition. But for the time being, as long as they're sufficiently close, what happens, you overlap the HOMO with the LUMO, you get a new bonding orbital. They mix together, you get a new bonding orbital and a new anti-bonding orbital. And even if the HOMO is not high enough in energy, higher in energy than the LUMO, this new bonding orbital is always lower in energy than the HOMO, and so that's how they move down in energy. So, and I think your question's really interesting. You were saying, I'm not sure how this works energetically. Probably you are worried about the fact that I go from two things that are neutral and have bonds to two things that are, one that's positively charged and one that's negatively charged, and I lost the pi bond. It turns out you're right to be worried about that. This reaction, reaction number one, is actually uphill in energy. And we will talk about why. That's going to come later. This second reaction, though, is downhill in energy because you now go from something that didn't have a bond to something that does. Yep, so we'll deal with that, but we're probably not till we get to chapter 6. Good. All right, so supposing you wanted to take this product and do a subsequent reaction. Supposing I wanted to bring in a nucleophile. So I'm just going to say, let's bring in the following nucleophile. It's going to be this molecule with a negatively charged oxygen. There you would say that the HOMO of this nucleophile is the lone pair on the oxygen. So draw an arrow from HOMO to LUMO. Over here, again, because the LUMO is a sigma star, you have to choose which atom, carbon or chloro, gets attacked. So what do you think? Carbon. Why? Because chloro is more electronegative, so carbon should be electron poor. And you always want to attack the LUMO where it is most electron poor. So we attack at carbon. That signifies the formation of a new oxygen-carbon bond. Because this is an anti-bonding orbital, we must break the carbon-chlorine bond. This arrow signifies the breaking of the carbon-chlorine sigma bond. Two reasons you know that bond must break. First, you're filling the LUMO, which is an anti-bonding orbital. And second, if you didn't break it, you'd have 5 bonds to carbon. And even in the great state of Texas, carbon only forms 4 bonds. We call carbons, jokingly organic chemists call carbons that you draw that have 5 bonds to them, Texas carbons. Yeah, don't know why, but that's just what we call them. Everything's bigger in Texas except carbon, which still only forms 4 bonds. So no Texas carbons. All right, so the product then is, here was my nucleophile, here is my new sigma bond, and here is carbon 2 and carbon 1 from my original alkene. And folks, we just did our first synthesis. We started with 2 things, and we made a new product, and then we used that product in a third reaction. Organic chemists love to do this. Synthesis allows you to make molecules of increasing complexity from very simple starting materials. By the way, this reaction that we just did is called a substitution reaction because the chloro here got swapped out for the nucleophile. In other words, before the reaction, chloro was attached to carbon 2. After the reaction, this oxygen group is attached to carbon 2, and we call that a substitution reaction. Yes?
Is there a reason to label the carbons 2-1 on that?
Yeah, because I drew the molecule kind of funny. I need to communicate that oxygen bonds to carbon 2. Carbon 2 used to have the chlorine. Yeah, go ahead.
The only difference between the addition and the substitution is we have, obviously the addition was adding the Cl, and then because we chose to decide the conjugate base of an alcohol, which is going to take Cl, well, it's going to take the H off of that, and Cl is going to be by itself.
So you said in the addition reaction, notice we add two things. First, a new carbon-hydrogen bond here. Second, a new carbon-chlorine bond there. Now, when this nucleophile, in the next step that we do, and we could isolate this and move on, I was just saying let's now do a third reaction. If I introduce this, then yes, the negatively charged oxygen could attack the carbon-chlorine antibonding orbital. Now, I heard you say something about taking the H off, and there is no removal of hydrogen here. It's just oxygen attacking the carbon. Yep. Okay. I want to do, yes, go ahead.
So when that chlorine breaks off, it takes those 2 electrons in that bond.
That's right. When the chlorine breaks off, it takes the 2 electrons that were in that sigma bond, and they are now a lone pair on chlorine. Because chlorine left with its electrons, we are going to call it a leaving group. Okay. One more, go ahead.
Did you say substitution synthesis?
This is a substitution reaction. Overall, though, stitching 2 or 3 reactions together, that's an example of synthesis. Yeah. All right, I want to show you just maybe one more homo-lumo example. There's some others on your problem set. This one is maybe a little bit complicated, and this is an example that comes from 352. There are some cases in which the HOMO and the LUMO are in the same molecule. So if I look at this molecule, I've got a lot of lone pairs. I've got some on the oxygen and some on the chloro. Now we're going to deal very soon in chapter 2 with how to determine which lone pairs are higher in energy than others. That's the same thing as asking which is the strongest base. But for now, just know that having the negative charge on the oxygen is a pretty good bet that the lone pairs on the oxygen are the HOMO. Looking at the rest of the molecule, I don't have any pi bonds or empty p orbitals. So if I had to pick a LUMO, this would probably just be the carbon-chlorine sigma star. And if I drew that, here's what it would look like. Small lobes pointing towards the node in between the nuclei, large lobes pointing outward. So there's my carbon-chlorine sigma star. Notice that in this molecule, I have the lone pair, the HOMO on the oxygen, adjacent to the sigma star. In a molecule, when I have a HOMO on an adjacent atom, and it's adjacent to the LUMO, I can do what's called an elimination reaction, where the electrons in the lone pair, the HOMO, attack the sigma star. The new bond we form here is no longer a sigma bond because the oxygen and the adjacent carbon were already in a bond. So the bond we form has to be a pi bond. Nevertheless, because the LUMO was a sigma star, we have to break the carbon-chlorine sigma bond. And the products are going to be this. Here is the new pi bond between oxygen and carbon, and there's Cl minus, again, as our leaving group. The 2 electrons that were in the carbon-chlorine bond are now a lone pair on chlorine. Yeah?
Can you remind me how you decided that the lone pair on oxygen would,
Yeah, I decided that the lone pair on oxygen was the HOMO simply because the oxygen's negatively charged. Again, we're going to give you some tools in Chapter 2 very soon to determine which lone pairs on which atoms are higher in energy than others. For now, the negative charge is your giveaway. Yes?
I'm gonna be honest, this looks a lot, without the label, this looks a lot like resonance because of even the way that the electrons move. So how are the ways that we can tell these arrows apart?
So this looks a lot like resonance arrows, and I agree with you. If I were to draw something like this, you could have drawn a resonance structure by doing something like this. Notice the difference, though. This arrow is the same. This arrow is a pi bond going out onto the oxygen. Nothing's leaving. No sigma bond is breaking. No, there is a bond being broken in resonance in the sense that it's the pi bond. Here, it's a sigma bond being broken. So that's the difference. The other, this is esoteric, the other reason that resonance arrows are different from here is because in resonance, the electrons, though we draw the arrows, the electrons, here's the secret, aren't actually moving. Instead, this molecule is actually a hybrid structure that looks like this with partial double bond character between the oxygens and partial negative charge on both of the oxygens. Yes, and also this double-sided arrow. Yep. Okay, did I see? All right, one more thing about, oh, sorry, thank you.
Yeah, just a quick question. So previously when we had nucleophile and electrophile, then meeting made that reaction happen.
Yep.
But on this one, it's a single atom. So how does that like initiate?
So how does this initiate? The question, it's an excellent question, and the answer is this is actually an intermediate that you get from another reaction. Do you want to see it real fast? Okay. So this is a molecule. You're going to have some questions about this, and I'm just going to punt on them until you get to 352. CH3 minus, I'm going to put those in quotation marks. That's not actually what it is, but it reacts as though it were. You get this intermediate from CH3 minus attacking the pi star and breaking the carbon-oxygen bond. So anyway, you're right. That's an intermediate that we get from something else. Yep. Yes?
So would you call it an electrophile or a nucleophile?
Would you call this an electrophile or a nucleophile? You would say a nucleophilic part of the molecule reacts with an electrophilic part of the other of the same molecule. It's an intramolecular reaction. Okay, one more thing on HOMO-LUMO. This is something that somebody asked at 8 o'clock, and I think some of you have this question too. This is from your problem set, and I had you use a molecule that's called a carboxylic acid and another molecule that's called an amine, and I showed you the products of the reaction. And some of you looked at that and you said, what the actual heck, to quote my children. And what appears to have happened here, if you look at the products, is that this OH bond that the lone pair on the nitrogen attacked the hydrogen, and we broke the oxygen-hydrogen bond. And those are the arrows that explain these products. And if you were going to explain that, you would conclude that the HOMO on the nitrogen-containing compound was the lone pair. No controversy there. But to explain the electrophile, you would have had to conclude that the LUMO was the oxygen-hydrogen sigma star, when instead your process for identifying HOMO and LUMO would have told you that the LUMO was the carbon-oxygen pi star? Some of you had that question. If you didn't, now you do. You were not meant to predict what would happen here. That is why I showed you the products. Okay? I agree with you that if you were looking at this and weren't given the products, you would have concluded that the LUMO was the carbon-oxygen pi star. The fact that something else happens here tells you a couple of things. First, sometimes in molecules you have empty orbitals that are competitive with each other in energy. That is, maybe the pi stars here and maybe the oxygen hydrogen sigma stars right here. And so sometimes you will see there are multiple ways a molecule can react. Yes?
How do we know the pi bond is bonding or antibonding, not bonding?
So you know the question is about the pi and the pi star. If you have a pi bond, you have a pi bonding orbital and that is filled, and then an empty pi star antibonding orbital. So the pi bond is full. Let's just, energy diagram. The sigma bonds are down here. The carbon-oxygen pi bond is here. There's non-bonding lone pairs on the oxygens. Then here's the pi star, and then here's the sigma stars. This is the pi bond. This is the pi star. I think where you're getting confused is you thought I'm talking about the pi bond when I'm actually talking about its empty anti-bonding orbital.
Yeah.
So whenever you have a pi bonding orbital, there is also an empty pi star that's higher in energy.
Yeah.
Yeah?
Will we get to the part in the class where there'll be like a triple bond or a double bond?
The question is, what if there's a triple bond versus a double bond? I'm going to punt on that one till we actually encounter it, if that's okay. Yeah?
Does this happen like the proton transfer because carboxylate is stabilized by resonance?
Right, great question. So does this happen, the proton transfer? Though that language, proton transfer, means literally we attack the hydrogen and it now is transferred to another molecule. This thing that's left is called a carboxylate, and the question is, does this happen because the carboxylate is resonance stabilized? You're pointing out that I could draw a resonance structure that would look like this. Yes, in part, and we're going to talk about that. So for right now, as long as you recognize that what happened here and came up with, gee, that's weird that the OH sigma star is probably the LUMO here, that's fine. And if you're uncomfortable with it, that's fine. I wouldn't have asked you to predict this yet. The point is, when you get in a situation where you have multiple things that could be the LUMO and they're somewhat competitive with each other, one good rule of thumb here is that hydrogens are smaller than carbons, so they are easier to attack than carbons. But as to why the nucleophile prefers to attack the hydrogen than the carbon, we're going to give you some tools to recognize when this hydrogen is especially acidic or especially prone to being removed. Okay. So let's now, somebody during the first hour, what time is it actually? Can't tell. 2 minutes? Yeah, I could do something with 2 minutes. All right, during that substitution reaction, somebody asked this question. Is it better to have a negative charge on oxygen or a negative charge on chlorine? In other words, they wanted to know what the driving force for this reaction is. To know whether this reaction would be favorable or not, you really need to know two things. First, how strong is the carbon-chlorine bond versus the carbon-oxygen bond that we made? And second, how stable is oxygen with a negative charge on it versus chlorine with a negative charge on it? And that is essentially the subject of Chapter 2. Where are negative charges stable? Now that's concealed in the title of Chapter 2, which is acid-base chemistry. And right now, when you hear that, you think we're going to be back in Chem 106 calculating pHs and figuring out how to make buffers that are pH 7 by mixing a quantity of conjugate base with its corresponding acid. That's not what we're going to use acid-base chemistry for in this chapter. We're going to use it to compare how stable is this group versus this one. And I'll tell you real quickly, we're going to do that by looking at the conjugate acids, HCl versus this alcohol. And we're going to conclude that HCl is the stronger acid, and therefore Cl minus is the more stable conjugate base. So get started on that study guide 2. Try to get more than halfway through, and we'll push through and talk more about that on Wednesday. See you then.